Okay.
First, Leon, I have to say first that I'm very new to the subject, but I have two questions that I came up with during your talk. The first one is, as far as I understood, in the Minfield games, you have each agent in the whole game that has its own probability distribution. The response on the strategy is a probability distribution, or did I understand that correctly? Or
no, that's not the case. So all the agents, there is a to describe the whole population, there is a single probability measure.
sorry, the entire game or the response of the strategy for each agent?
Don't say, okay, so I mentioned game, don't think of games, think really in terms of Nash equilibria, okay?
Okay.
So it's really about the Nash equilibrium. So don't think in terms of strategy, think in terms of Nash equilibrium. Otherwise, it's going to be complicated. So in terms of Nash equilibria, each generic player is trying to optimize a certain criterion that depends on the whole population, and the whole population is described by a probability measure. Okay.
Okay. And
so Nash equilibria. Don't think about. I see what you're aiming at. You're probably interested or knowledgeable in game theory, but no, this is a little bit on the side. So don't worry about it.
Okay, that was probably, yeah, then I got it wrong. But then I have another question which is related to the correlation of the responses of the strategy. So suppose again, I'm probably going again in a different direction, but each strategy, each response of the agent is correlated to another one.
Okay, so if you wanted to see this type of topics, and again, I see what you're aiming at, it would be to the next question that we don't know how to solve, except in some cases, which would be to say, okay, so n goes to infinity, those Nash equilibria, we have a Minfield regime. Can we describe the fluctuations, and that's where the correlations between the actions of the various players in a finite game are going to play a role? Can we say anything about the fluctuation in this limit?
Yes.
So we can answer that only on very, very, very explicit examples. In general, we have no theory.
Okay, thank you very much.
Okay, other question? No? Okay.
Okay, thank you for the nice talk. So, sorry.
The MFG monster or whatever. Now, where does it come from? Is it clearly a model that everyone agrees on, or it comes from a limit analysis, or?
Okay, so it's indeed the limit as n goes to infinity of dynamical Nash equilibria for finite player games.
And you get all these equations by this.
You get all this. And the full justification as n goes to infinity has been done in situation where we know that the master or the monster equation has a unique solution. Okay? Then the limit as n goes to infinity has been fully justified.
Thank you.
I just want to ask a question. In physics, we start with the entropy, the statistical mechanism. So what is entropy in your theory? So you mentioned the generator. You don't.
There is no entropy.
So you just lead the generating function.
Yeah, no, I mean, again, this is I'm not sure I understand fully how entropy pops up in general. And so it's hard when you don't understand something, it's hard to answer a question about that something. But the way it's being used, which is not the same as how it happens, this I understand in, let's say, classical statistical mechanics or statistical physics, or the principle of thermodynamics, right? Which postulate that there is something like an entropy. So the question is, is there something like the entropy here? And that's a little bit dangerous because I think that in terms of information, we are in a totally different situation. Because indeed, we have like n particles, my players, which have a certain dynamical evolution, which is fine. This is consistent. This could be consistent with thermodynamical equilibrium and so on, but they are not particles, they are agents, which means that they anticipate. And so the arrow of time is completely screwed. Forgive me for the expression. So it goes forward in time because that's the evolution of a system, but it goes backward in time because choosing is about anticipating. So this might explain why we have never experienced any kind of entropy playing a role there. Okay. So forward, backward. And that's anticipation, and that's absolutely crucial. Now, anticipation comes with a certain depth. You know, so when you reduce that depth, in the sense that it's the so-called intertemporal preference rate, which measures how important the future is for your today decision. So if the future is as important as the present, okay, there is real anticipation. But if somehow you discount the future so fast that essentially all the present counts, what you get as a limit of Minfield games, just reducing the anticipation to now, you get agent-based models, classical agent-based models. The decision is being made instantaneously. Okay. Then, if the decision is being made instantaneously, you're going to see entropy functionals playing a role. But with anticipation, I've never seen anything like, inspired by entropy. But I might be wrong, since I don't understand the entropy.
Yeah. Other question?
Yes.
Yeah, please.
Greeting, Professor. I'm also an undergraduate physics student, so here I got some questions naturally correspond to physics-like questions. So in the first case of the towers and beach problem, can I understand this is
I'm sorry, the what?
the towers in the beach problem?
Yeah.
Yes. Can I understand it as there's a bunch of particles in the box. Maybe they are repelling each other's or they are just attracting each other's. So naturally, the equilibrium would be either the homogeneous distribution, either they are just boom together. So this is the first question. And the second question is correspond to that what you have mentioned. There is no no time in the game with respect to the particle case. I'm not really get it. Could you please explain it more? And the third question is there any phase transition in the game?
Okay, so very good questions. You could give a posteriori when the criterion is a gradient and interpretation like particles for the towels on the beach. In general, if I take my G and I keep epsilon strictly positive, you can prove that there is no single optimization problem that yields this equilibrium, which means that you cannot obtain it by any kind of classical particles or quantum particles because you're going to have an energy minimization principle. So the answer is different. Okay? And the fact that they choose, that they anticipate means that it's completely different. Now, your second question is about phase transition, which was in fact evoked with the big question marks, fluctuations, phase transitions. I have no clue. Clearly, from a physics point of view, let's be frank, Minfield theories are boring. Okay? That's simple. It's well known. Okay? In the context of game theory, Minfield theorems were not known, so it's a new world. The next step should be about, one can dream that there will be one day a next step about phase transition, which in some sense would explain how you go from one place of interest on the beach to the other, when you're going to switch from one to the other, what kind of transition to take place. And here is part of the difficulty which makes the difficulty, the fact that we are dealing with games and so on makes the problems intractable for me now. The point is the following, is that as you well know, Mean field series are possible because you have weak interactions. Okay? In order to have this type of phase transitions, you're going to have to go beyond weak interactions. And that's a serious, serious problem, because what does that mean in my terminology? And that's consistent with what we can observe, in that here I had a crowd of small agents. Weak interaction because they're automatically small in some sense. Now, if I want to explain phenomena like, brutal transitions and so on, I need to invoke at least a few big players, which are going to guide the rest of the population. All of them being good, being big, or at least a few big ones. Maybe. But I have to go beyond weak interactions. And this, we don't have any kind of mathematical tools to begin that story now. It will come, but another life.
Other question? There.
So how do you solve the mean field game on computers? I guess
numerically. Very good. Excellent question as well. We do what we can. Okay, so in one of the transparency, I went very fast. There are 3 types of numerical. We have basically 3 types. Worldwide, there has been 3 types of numerical methods which are available. In fact, that was the first question that Bob Lucas. I remember I gave a small private talk in front of all the Nobel Prize winners in economics in Chicago and the other professors. It was very, very impressive. The guys were picking the ideas incredibly fast. And at the end, Bob Lucas said, "Oh, that's cool. How do you compute those stuff?" And I said, "Well, we do what we can." Was disappointed. But anyway, so we have 3 types of proofs. One is really a full discretization and Newton methods at the level of discrete model, brutal. And the discretization is being made in a very careful way, so to preserve some kind of conserved quantities. Okay, that's one. So typical finite elements, but we do very carefully the discretization. And then you have a nonlinear system of ordinary differential equations and an iteration by essentially Newton-like. Okay, I would call this brutal way. Okay, then there are other ways which are some very specific iteration, like guessing what M is, getting the U, getting the M, getting the U. This in general doesn't converge, but in some cases you know how to handle those iterations. So it's an equilibrium, do fixed point arguments. And the third thing is to introduce another time, which is like the learning time. So like a relaxation time. So you add one more variable, so it's very heavy. Okay, so suppose that you have already a two-dimensional, two variables to describe a player. You have the real-time variable, and you introduce another time. It becomes a 4-dimensional problem. Okay, so it's very heavy. It's like a Desperate method, but this is a very, very stable method, which in some sense creates a deformation towards an equilibrium. In general, given a totally new problem, we may not be able to make the computation. Fortunately, there is a fourth method, is that in some cases we can reduce the problem to the optimal control of a partial differential equation. And the forward-backward nature of the problem becomes the optimality conditions for the optimal control problem in PDEs. Okay. So then you solve the optimization problem, which is the optimal control problem. Sorry about this long answer, but I'm giving the full details. So for methods, given a model, we may not be able to solve it numerically, to be honest. Until now, we have always managed, doing what we can, to use one of the existing methods and twist it a little bit and make it work. The even worse part is how to make computation in infinite dimensions. Cressel Smith, again, those two guys, what did they do? They made a description, so the noise that kind of shocks, what they call shocks, which make the infinite dimensional problem, were happening from time to time, and then the population would switch to one state to the other in terms of work production and consumptions. It was this type of macroeconomical problem. So they set up, and this depends on the state of the whole population. So they wrote a set of rules explaining, depending on the set of population, each player will do this and that, without writing more than this, and then they made a numerical computation, infinite dimension. It's incredible. Huge, massive Monte Carlo simulations. They cannot compute the full measure, so they did a moment-based description of the measure, computing the first 10 moments. And they had this conclusion out of the numerics. That's why economists didn't understand anything about this paper. And the conclusion was that 90% of what they were getting depended only on the first moment of the probability distribution of the population. So the bottom line is that they had a very crude approximation method, and we have been working very, very carefully about hierarchies. It's like a tree-like approximation of this infinite dimensional problem, where basically you have at some times, which are in some sense random, it's a Poisson type noise, you have shocks. So it creates like some kind of trees, and we make computations which are very, very heavy computation. The guy who is really in charge of the best numerical development in this community is Yves Ajdou in Paris, former student of Olivier Pironneau. That's a long answer to your question, but it's difficult.
Okay.
And we do what we can.
So we have time for 2 or 3 additional questions, if there are still some questions. So if not, so let's thank again Professor Lyons.
Oh.